Uh, Again, thanks a lot to everyone for attending the workshop. So my talk is the last talk of the first week. So hopefully all of you have been enjoying the workshop so far, and we really hope we can continue this. Thanks, Chetan, for wonderful arrangements. And today's talk, I told Chetan that I wanted to do something that was more of a tutorial flavor so that a lot of the students in the audience can get started in this area if you are not in this area already of in-memory computing. But then after talking with some colleagues, I realized I should also put in some of the recent work that we have been doing. So maybe the second half of the talk, I'll talk about some of the stuff we did last year. Okay. So let's get started. So firstly, why in-memory computing? Okay, so I like this slide, which was 2014 ISSCC talk by Mark Horowitz, where he was talking about the energy of computing. And you look at this one, 32-bit additions or 32-bit multiplies. Let's look at multiplies because we need multiplies a lot for neural networks. It takes about 3 picojoules. And if you look at the energy needed to get the operands from memory, so this is cache, which is on-chip memory, you need about 100 picojoules for each operand. Right? So that's like 30 times more energy to get the data. So computing then is free, right? Don't need anything. If you have to go off-chip, if you have to go to DRAM, order of magnitude more. Right? So even if you're on-chip, big memory, getting data is very expensive, energy-wise. And you see the interesting trend is the same bit of data, if you're getting from a smaller memory versus bigger memory, you pay a bigger price. It's not getting more data, it's the same 32-bit data. And these days, you have seen variants of this plot. The model sizes are just exploding. So more and more memory. So this problem is more and more important. Oh, this one was for a very old node, 45 nanometer. All these 45 nanometers. This is 2014. So it's old talk. But still the same point. So that was about energy. The second one is about how fast can you get the data, bandwidth. So this one is talking about, this is time again. This is looking at different aspects. This is flops, how fast can you compute. These two, this one is bandwidth from the DRAM. This one is interconnect. How fast can the wires send the data. So basically what we are showing here is the computes is growing much faster than the interconnect. So it's like, you have a lot of data in memory. Memories are growing big. You have fast compute, but the link between the two is still very weak. Right? So it's like you're in a bottleneck. That's what's going on. Right? So you have energy, you have throughput, both being bottleneck. So if I come back to this slide about the memory access energy, and then I motivate, conventionally then what we used to do is we would take data from memory, process, get an output and write back to memory. Right? That's the conventional one. We showed you that's bottleneck. So that's why a lot of people try to move towards something called near memory computing, where they try to put the memory close to the processor, have high bandwidth connections on top of the processor and so on. That helps you a little bit. But the most radical version is you have the input, the X that you want to compute, directly going to memory, and you only read out the final result. So everything is happening inside the memory. So that is why we call in-memory computing. Okay, so you're doing computing inside the memory. So a little bit more detail, again, this is a tutorial, right? So I go into a little bit more detail. So look at the standard computing that you do for many neurons, right? You do something like this, it's like a dot product, right? Sum over Wij xj. And I need to, so I'm summing over k inputs, and I'm creating k such outputs. Okay, so there are k squared number of weights in this network. So if I'm storing the weights in memory, and the x is going to the processor, in normal serial processing, what happens? You read out the first weight, W11, multiply by x1. Then you read out the second weight, W12, multiply by x2 and sum with the earlier one. So you're creating these partial sums, and you need k cycles to read out these k weights, create this first output. Okay? And you need to do the same thing for all these k outputs. So the time required is order k squared. Now you can do a little bit fancier. You can say, okay, I'll read out the entire row in one cycle. So you can read it out parallelly. So in that case, I make the processor big, assuming that I can handle all the data. So in first cycle, then I can do this first output, Z1, W11 X1 plus W12 X2 plus so on. Second cycle, I do Z2 and so on. So in this case, I'll need order K because of the K rows of this matrix. Okay? Contrast what we are proposing here, what we're going to talk about. In-memory computing, the X is directly going to the memory. Don't have a processor. What you're reading out in parallel is Z1, Z2, Z3 till Zk. Time is order 1, sort of constant time. Okay, so clear the difference? So it can really help you in many cases. Okay. So what's the neuromorphic connection? So, I think a lot of the people here already know about this. The original paper from Carver-Mead, which talked about neuromorphic, talked about analog signal processing or physical computing. So, I mean, I call that the neuromorphic version 1, the original definition for circuits, where you have hardware, physical hardware that's doing the computing for you. So since then, last maybe 10, 15 years, the term has kind of broadened a little bit. Talk with people in computer architecture. They will talk about non-von Neumann architecture, where memory and computing is mixed, is also neuromorphic. You talk with people in computer science who are doing algorithms, and they'll say that if time is intrinsic to computing, if you have something like spiking neural networks, that's neuromorphic computing, and so on. Yeah. So in that sense, when I talk about in-memory computing, by the way, sometimes in literature, this is also flipped around and called computing in memory, so CIM. So analog SIM actually uses analog processing inside the digital memory. Okay, so it is definitely neuromorphic in the original sense of the term. Secondly, I said computing is happening inside the memory, so memory and computing are definitely mixed together. So it's also neuromorphic in that sense. It's not it's a non-von Neumann architecture. And lastly, if you are doing SNNs, a typical equation that people do for leaky integrated fan neurons is something like this, where you again have this kind of a weighted synaptic summation. This again clearly maps to the same kind of equations I showed you. Only difference, the input x's are now binary spikes. Okay, so you have a spike vector, which is a binary vector. Okay, so that's basically the neuromorphic connection, and hopefully all of you are convinced that I can discuss this in a neuromorphic conference. So now the next slide is about types of in-memory computing. I talked about analog SIM in the last slide. There's also digital SIM. Okay, so if you look at papers recently, there's a lot of people talking about digital in-memory computing. What is that? That's basically doing something like this. If your operands are stored in memory, you can enable, let's say, two of these lines, two of these memory cells, and you can show this is for SRAM. The computation that happens on bit line and bit line bar is basically an AND operation and a NOR operation. And you can actually map most operations in digital, like additions, to these two fundamental compute units. Okay, this is the XOR operation. You can map it this way. The sum is basically an XOR operation. Carry out of a digital adder can also use these two things, the XOR and this A and B, to create the carry out. So in digital in-memory computing, what people do is they will enable two of these rows at a time and do some computing at the periphery, then go to the next row and so on. So why are people even looking at digital computing? So this is a comparison between analog and digital computing, compute in memory. So analog SIM typically has higher energy efficiencies, right? Because I'm doing everything in parallel. Here I'm doing only two at a time. But the problem generally that people talk about is if you're going to very large scale chips, you have these process variations, voltage variation, temperature variation, which we summarize as PVT. That limits generally the number of bits, the precision that you can get using these computing. Typically 6 bits, sometimes 8 bits, that's generally the limit. But for these digital systems, you can keep on increasing the precision by adding more and more clock cycles and bigger adders. but of course they have limited energy efficiency. So as we would expect, they're kind of pioneered and being pushed by TSMC, and this is sort of their papers at ISSCC if you see over time. So they're going from 22 nanometer to 5 to 4 to 3 nanometer and so on. Why? Because these digital circuits really scale very well. So as they're going to more and more advanced nodes, a lot of these extra circuits are actually shrinking very well, whereas the analog SIM cells don't shrink so well. Okay, so of course they are doing what they are very good at. But so for this talk, I will not focus so much on digital SIM. I will focus more on analog SIM because I like analog. I'm an analog designer. Also, this is in spirit of the neuromorphic approach. So for this particular talk, no digital IMC, it's analog IMC, okay? But if you're interested, we can have a chat afterwards. Okay, so let's start with some non-volatile memory basics, and I'll talk about how you can do SIM using non-volatile memory first. And that's also where I started off. So. Okay, so it's a simple neural network, 3 inputs, some weights going to few outputs. Easiest way to understand this approach, I think, is if you think about resistors or conductances representing each of these weights. Okay, so I have inputs coming in along the rows, and I have wires coming along the columns, which are producing these two outputs, Z1, Z2. How is this happening? So suppose these amplifiers that I show here, which are basically like transimpedance amplifiers, are pinning this node, let's say, to ground, 0 volts. So think about the voltage across this conductance, X1 minus 0, right? So it's X1. So what will be the current flowing here? Conductance times voltage, right? So the current here will be this conductance, let's call it G11 times X1. Okay? It's very easy, Ohm's law. Similarly for the next one, G12 times X2, G13 times X3. Now see, all of these are tied together on the same line. So the next thing that you do is, you invoke Kirchhoff's current law, KCL, and you say the currents are going to sum together. So the total current coming here is something like this. Sum over G1I times VI. And you see, this is very similar in format to what I had here for this neural network equation for basic neuron. So now we have some more details. Why do I have two things coming here and then subtracting to get Z1? It's because the weights of a neural network can be positive or negative. Conductance can only be positive. So basically now you represent a weight as difference of two conductances. Then I can get positive and negative. And yes, yeah. Very, very true. So that's a circuit question. Generally, when you have a transimpedance amplifier, what happens is the capacitance on this line is generally pinned to a value. The transimpedance amplifier does not let the voltage change. So even if there is a capacitance, it's not going to get charge or discharge. But of course, it's limited to the finite gain of the amplifier. Yeah, of course. So all of those will be there. So here I'm not going into the dynamics at all. I'm assuming everything is settling. So the time that I'm giving to the circuit, allowing the transimpedance amplifier to settle. So yeah, true. So pure digital case, those issues won't come in, but then you will, again in the pure digital case, you cannot do this fully parallel computing. You can only do 2 at a time because you are doing logic operations. So it's a trade-off. Yeah, so here what I'm showing is this transimpedance amplifier outputs are getting subtracted out, right? Now, the subtraction you can do in n number of ways. If you are doing current mode, you can use a current mirror to mirror the current and subtract it out. A lot of people do separate ADCs on the 2 lines and then subtract in digital. So you can do a variety of approaches. Yeah, so that's because conductance 1 minus conductance 2, G1 minus G2 is proportional to the weight that you want to map. So in the easiest way, what you can do, a lot of people do this, is if you have positive weights, you just program this resistance. Don't do anything to this one, this is 0. and you have negative weights, you program the other side, don't do anything to this one, this is 0. That's the easiest way to do it. Okay, so now if you look at it, what we have done so far is resistive memory. So basically each of these resistors or conductances is now one memory cell. Okay, it's a tiny memory cell in the big array. You can have digital or analog mode. So in a lot of industry work, people are using these resistors to store digital bits, zeros or ones. Okay. Why? Because that's more robust, and a lot of these devices don't show analog switching behavior. You can't have many states. A lot of these devices only have 2 states, so that's what they can do. Okay, so and we talked about 2 devices for bipolar weights. Okay, the multiplication is by Ohm's law, accumulation is by Kirchhoff's current law. So fundamental physics. And basically one of the good things about these devices a lot of people talk about is they're very area efficient. So if you look at this picture, this is one set of metal lines, this is another set of metal lines in the CMOS process. A lot of people actually fabricate the devices between these 2 metal lines. Okay. So in that sense, it's not even using active silicon area, it's on top of the silicon. Okay. So that's a good thing. And if you see here, the voltages are encoding the input value, right? Input encoded as voltage, but that means yeah, you need, yeah, of course, you need right circuit. No, you will need some, so basically what happens for any memory device, any non-volatile memory or volatile memory, you need some circuits for write, some circuits for read. The operations that I'm talking about are more read operations. That's in inference. If I do learning, then the write also comes into the picture. That's one other level of difficulty. Yes. Okay, so I will show results, measurement results from a memoristor chip with many states. That's possible, but if you do a wider literature survey, you will see most of the industry devices that people are selling for RAM, PCM, and so on are binary. So the ones you're talking about are, okay, not in production, the analog RAMs. Okay, so one of the issues with this is if I'm encoding voltage as input, I need a digital to analog converter for a digital input going to voltage, and that is expensive. Okay, you can't generally do it very well pitch match to a digital memory array, because memory arrays are very dense, very tiny cells. A DSC, if any of you have designed it, is generally quite big. So that's not very friendly in that sense. Also, generally with process scaling, the voltages, power supplies are going down. So you do not have too much dynamic range to place these voltage levels. Okay, so that's another issue. And lastly, something that I did not talk about so much is because you have resistors, each of the resistors will draw current, right? That's how we are computing. So now these drivers have to push all of these currents through this entire row. That means it needs a very strong drive. And that means it's again not an easy design for this DSC. I will. ADC will be a large part of my talk, so just hold on. So this is going back to some early RAM devices where you have this conductive filament formation in oxide devices, and that's how people think you are getting these different states. And yeah, you can have resistances in the middle if you have some half-formed filaments. Generally, the right process that you were talking about is something like this. You give some pulses, positive pulses, to set the device to a high conductance state, negative pulses to reset the device to low conductance. This is a binary RAM. So you can see we have 2 states mostly, right? So on state, off state, and you have some variation even in those states. Okay? So normal digital bit SRAM, if you say 0, that means really it's 0 in all the cells. Here, if I say it's a 0, it's not really 0. Can you see there's a big spread in the resistance? So it's not really a true 0. And what you need in these write processes, generally you need some read and verify processes in the middle. So you do a write pulse, then you read it to see whether the actual thing has been written or not, because there is some stochasticity in the write process as well. So not very easy programming the devices. Okay, so now going into array architectures. Typically, in CMOS, if you have worked with transistors, if you turn a device on, put VDD on the gate of an NMOS and put 0 on the gate of an NMOS to put it off, the ratio of currents is very big. Okay? I on to I off is like 10 to the power 10. These devices, 100 to 1000, okay? Not big ratio of on to off. What does that mean? So if the ratio of on to off is only 100, think about it. I have a column of 100 off devices, and then when I'm reading the current, it looks like, oh, there is one on device. You see, so that's a problem. So I can't make very big arrays just because of this reason. Okay? So what people started doing, they started coming with a different architecture. They need something called a selector device, where you see this additional MOSFET in series with this resistor. And because the MOSFET has a big on to off ratio, you can use this to select these resistive devices very nicely. So then even if this resistor in off state is not very off, the MOSFET can totally cut it off. Okay? And then you can make much larger arrays of these devices. But now you see the input now comes on the gate of this MOSFET. If the input is coming on the gate of the MOSFET, I cannot change the voltage there and encode my input. Yeah, because I'm using the MOSFET as on and off. So what to do? So then what people started doing was they started changing the pulse width or the on time of the MOSFET to encode the input. Okay, so the longer time the input is on, longer time the device will give current on this bit line. Yeah. No. No, so what will happen is you will have all the word lines having these inputs, these pulse widths coming in parallel. You don't have to do them in series. It's still parallel, but the encoding of the input is now in time. It's a pulse width. So that seems easy with digital circuits. For example, if I have a number 1001, that just means I need to turn this word line on for 9 clock cycles. So that's easy. I can do a counter and stop the counter whenever I hit that number, right? The other advantage is this is now tied to gates of transistor, so it doesn't have to drive a lot of current. So these are very good. And also there is no dynamic range issue because the signal is not encoded in voltage, it's encoded in time. And as you go into more and more advanced processes, transistors are becoming faster and easier to encode time with high precision. So all of that seems to be a good thing. But I'll come to one bad thing about this encoding in a later slide. Let's see. Yeah, yes. Yeah.
So now in series to the memory resistance, transistor on resistance is also coming into picture.
Very good. It's also coming into picture, but generally the way you have to design this is the transistors on resistance should not have too much effect.
We are expecting a memory kind of a behavior on those mem resistance, while the static transistors will always reflect the static on resistance. So how are we actually programming?
Yeah, so that's what I mean. So if the on resistance of the transistor is going to be a lot less than the range of resistances of your memristor, then you can think of that as a small perturbation to your original memristor conductance. Yeah, just lift the baseline.
From input to output, input is given at the gate, right? Because of the MOSFET, there will be non-linear behavior from input to the output, right?
If you think the MOSFET just acting as a switch, because it's just on and off now, no analog voltage is not going there. So it's a digital voltage and the signal is encoded in time. So if it's just on and off, then it's whether the resistance is connected.
Product is the current times the conductance, right?
Yeah, so now I did not show the equation. What will happen now is you have current times conductance times delta T, which is the time for which this thing is on. Yeah. Yeah.
But the mapping from the input to the output current, previously we had only the conductance, but because of the MOSFET now it will be non-linear.
No, what will happen is here you had G times V, right? Here the input was encoded in VI. In that case, pulse width, what will have is VDD times delta TI. So basically the time that signal is on, that's gonna encode your input. The MOSFET is just on and off. So it's not in an intermediate state. So only the on resistance will play some role. Yes.
Yeah, yeah, the previous slide. So with the insertion of this transistor, now the gap between the zero state and the 1 state, suppose it's a binary resistance, will also be lessened, right? Because of the active BDS of the transistor, that voltage will also be accounted. So this gap will come even closer.
Uh,
The dynamic gap between 0 and 1 states.
so ideally the resistance in the off state of the MOSFET is very small conductance or very big resistance, whichever you want to. So that will actually push these two curves far away because the off resistance of the MOSFET is very high. So it's going to push the off part higher. That's the reason you're doing the selector. Yeah, so for example, if you had a digital value of at the outputs, okay, what happens at the outputs here, now you don't have a trans impedance amplifier. Instead, you have a, let's say, a capacitor that's integrating the current that's coming in. So then you can see that the delta V on the capacitor will be proportional to how much charge goes in. And the charge that goes in will be proportional to I times delta T for each of these devices. And that delta T is your X. Yeah. Okay, so I think I'm running very short in time. Let me just quickly go over. So this one is another sort of non-volatile device that we used to work on a lot. It's called a floating gate or a flash device. Now here what happens is it's a 3-terminal device, so it can already act as selector plus memory in some sense. Okay. So let me just skip over this one because I have a lot of stuff to cover, and you have programming methods for these, and you can again do similar vector matrix multiply using these devices. Okay, so let me now skip over to the other part, which is volatile memory devices like SRAM and EDRAMs. So these are again very commonly used. I say EDRAM meaning embedded DRAMs, which are inside your chip, as opposed to DRAM, commodity DRAM, which is outside the chip. In this talk, again, interest of time, I'm just going to focus on SRAM, but I'm happy to discuss EDRAM later on if you want. We have many works in that space as well. Okay, so pros and cons, volatile versus non-volatile. Volatile memory is there on every chip, right? Any computer chip, you have cache, right, which has a lot of SRAMs. It's very stable technology, studied for many years, decades. And Chetan talked about write. These have much lower write energy compared to non-volatile memory. So if you are doing learning systems, potentially SRAMs might be better because you can keep on writing to them. The non-volatile devices, larger energy, also there's something called endurance. They can stop working, cannot be programmed after certain number of cycles. So the cycle number is long, but still, it's an important thing to keep in mind. Flip side, negatives, only 1 bit per cell. So generally one SRAM, 6 transistors, source 1 bit. I was talking about, RRAMs or flash. Each cell can store ideally an analog value, many bits. So there is, of course, an area overhead if you're trying to do multi-bit weights using these kind of SRAMs. Okay? You have to combine many memory cells together. Producing the multi-bit output, this combination is also non-trivial. Okay? And lastly, of course, it's volatile by definition. So if you are putting it in an IoT device where there can be power fluctuations and the SRAM data gets corrupted, you have to rewrite entire weight into your device again. Okay, so with that in mind, let's quickly take a look at some SRAM in-memory computing devices. Just again, it's a tutorial. So basic SRAM cell is like this. So you have 2 back-to-back coupled inverters that creates a latch that can store a state. And you have 2 access devices which are turned on using a word line. And then you have these 2 bit lines, bit line and bit line bar, that is used to sense the data in the cell and also to write data. So generally the writing process, you have some drivers which will write data into it. reading process is more of what we are interested in for in-memory computing. So the read process is a bit like this, where you will first pre-charge both bitline and bitline bar to power supply and then leave them floating. So they are now like capacitors holding some charge. And then you enable word line of the row that you want to read. So these two transistors get turned on. NMOS transistors. So suppose the cell is storing a 0, then for this NMOS, gate is high, it's on, source is low, so its VGS is high, so it starts discharging the bit line. Okay, so this bit line voltage will start falling down. Okay, this side it's a 1, so this NMOS there is no VGS as such, so there is ideally will be no discharge current here, bit line bar will still be high. And generally you have something called a sense amplifier, which is like a comparator down below here that senses the difference between these two voltages and tells you whether the cell was storing a 0 or a 1. Okay, that's basically how SRAM operates. Now, what's the difference in regular SRAM operation versus in-memory computing? Regular operation, only one word line is enabled. What you were talking about, Nimrod, that you have one row at a time kind of a read. Major difference in in-memory computing is multiple word line is enabled. Okay? That's really the key of how you are getting the efficiency in throughput and so on. Input signal representation, we talked about it. Typically 1 bit, okay, because you typically give a short positive pulse on this word line to indicate your input. So 1 bit input is easy. If you have multi-bit input, what do? You can do pulse width modulation on this word line as well, or pulse frequency modulation, just number of different pulses. So both are possible. Just to give you an example, this is sort of a simulation. This will clarify hopefully a lot of things. Now see what's happening. This 6 transistor is storing the state. This access device is the one that is discharging this bit line and bit line bar. Yeah. So think about it. The gate of this device goes to a fixed voltage depending on power supply of your SRAM. So this kind of has a fixed VGS. So it's sort of acting like a current source. Yeah. And it's going to pull out some current from this bit line. So our first order approximation is current source. So it should be a constant current. But all of you know about early FFT transistors, right? So when you are pulling this bit line, the voltage is changing, the drain voltage of the MOSFET is changing, so VDS is changing. So actually over time, the current will also not be constant, it will keep on changing. So normally what happens, in this case, the power supply was 0.8 volts. We are showing that around 200 millivolts is basically the dynamic range that you have for this particular case, whatever accuracy they wanted. After that, the current has changed so much that you cannot treat this as a constant current source anymore. Okay? So your accuracy of computation is going to take a hit. So this is the maximum read bit line where nothing is discharging. This is the minimum read bit line, so about 200 millivolts. This shows you an example that if you are giving this negative pulse on the read word line, this is my input. If I have one cell enabled versus 128 cells enabled, you can see that the amount of discharge is sort of varying linearly. And that's how you're doing the computing. The amount of discharge voltage on the bit line is proportional to number of cells that are turned on. And this also uses the method I was talking about, okay? So delta V proportional to this discharge of a capacitor. Okay, so there are several ways in which you can use SRAMs for in-memory computing. The first one that I talked about is discharge of capacitors based on this current source. But you can see it has a very narrow dynamic range. So on the other side, people talked about other ways of doing this, where you do not discharge a capacitor, but you actually keep several cells turned on, several cells turned off, something like this. So a pull-up network that is fighting with a pull-down network based on how many inputs are 1 and how many inputs are 0. So in that case, the voltage on this RBL, directly the voltage is indicating your final output. And you can imagine this will be a little bit non-linear. This is a PMOS fighting with the NMOS. It won't be perfectly linear. But the advantage here is you have a wider dynamic range. You actually have 0 to VDD, the entire range that you can use to encode the signal. And then there's a third type of SRAM cells which actually put some small capacitors inside the BitRAM cell itself. What happens there is for 1 bit multiplication, you can show this is basically like an XNOR operation. So you essentially use something like a XNOR operation inside the cell, store the output on a capacitor. If the output is 1, the capacitor stores 1. Output is 0, the capacitor stores 0. Then in the second phase, you actually tie all the capacitors together for charge sharing, and then the final voltage on the bit line is the result of your operation, of your Mac. This is very linear because capacitive charge sharing is very linear. Yeah. This one won't, but the other one will, because here PMOS and NMOS are fighting together. This one will have huge amount of short circuit current. Yeah, that's a problem. So you have to only enable it for a very short time, read out your outputs, turn it off. No, of course not. They have designed it in that way. These devices are very tiny. So you have to be careful when you design these. Okay, so then of course we can compare pros and cons. Basically standard 60 cell that I talked about, the small size, limited, this is a good thing, right? It's a tiny cell, limited dynamic range due to this read disturb issue. But there's even bigger problem. Actually, I talked about limited dynamic range due to the early effect issue, but a bigger problem is this read disturb issue. I'll just explain quickly what that is. So you see in these cells, when we want to write some data into the cell, we also change the voltage on the bit line and bit line bar. Yeah. Now suppose one of these cells is storing a 0. Yeah, so then it was discharging. There is some other cell that's storing a 1 which is not discharging. So now think if the bit line is voltage is going down a lot because many cells in this column are discharging, then the cell that was storing a 1 will now see a very low voltage here. And this transistor will now actually start writing current into the cell. So what happens, this is called a read disturb, as a result of your read operation, because there are many cells getting enabled together, some of the on cells can actually write data into the off cell, turn it on. Okay, so that's a big problem with SRAM based IMC. So that's why people move to these kind of cells where you have what is called a decoupled read and write. So RBL stands for read bit line. You can see I'm sensing the data in the cell, passing it to a separate transistor to put it into this bit line. And I'm writing using separate separate bit lines, BL and BLB. So that's the advantage, it's entirely decoupled. Disadvantage, of course, you have more transistors, so you have bigger footprint. Last one that I talked about, the capacitor one. Advantage, low nonlinearity because it has capacitors. Disadvantage, the cell size is huge. If you have done layout, you'll know capacitors are pretty big. Okay? So then people do some tricks about these capacitors. They try to put a small MOS cap and then put a lot of metal caps on top so that you are not really taking a lot of this cell area. But still the cell size for this kind of devices are pretty big. So that's basically a trade-off. So no free lunch. Okay, so I think we are pretty much at halfway of the talk. So let me now switch gears a little bit and talk a little bit about some of the challenges and some of the solutions that we've been doing over the last year. Okay, so we talked about analog computing. In some of the small neural networks, you can actually have analog outputs from one layer directly go as inputs to the next layer. It's possible, but that's generally not a very scalable method, because if you want to make a bigger and bigger network, typically the kernel sizes often become bigger than what you can map to one of these macros. So then you have to go to some intermediate digital representation and then accumulate stuff and then go to the next layer. So you do need some ADCs at the output, which are analog to digital converters. And we talked about needing digital to analog converters at the input. We talked about digital PWM, pulse width modulation is a good option. But now there's a problem that we didn't talk about, which is for normal pulse width modulation in digital, if you're representing an n-bit word, you need 2 to the power n clock cycles. So that's a big latency. So even though I said order 1, it's order 1 in terms of the weights, but not order 1 in terms of bit resolution of the input and output. So you have to be careful what you're talking about. So a useful way people have devised to get around this problem is called bit slicing. Okay? Bit slicing. This requires only n input cycles for n bit input. No DAC is needed. So that seems good, right? So there's a but, and but will come later. Okay, so but what I mean by that is something like this. Suppose I'm doing x dot w. Think about representing this number x in its binary format. So x0 plus twice x1 plus 4 times x2 and so on, right? So which means if I have a number 1001, x0 is the LSB, then x1 is 0, x2 is 0, x3 is 1, okay? So you can split it up and then multiply with w. So it's linear, so you can do x dot times w plus 2x1 dot w plus 4x2 times w and so on, okay? So this is just expanding it. And now you can see what I was talking about, right? So what you can do here is you can, in the first clock cycle, just give x0, multiply with w, store the output. Next clock cycle, give x1, get x1 dot w, store the output. These outputs are in digital, and in digital, doing this summation is very easy because multiplication by 2 is just a shift operation. Yeah, so you can actually do that basically for free. You just need an adder. So this method will just require n clock cycles for n bit inputs. And that's a very popular approach these days for SIM. Okay, so challenges. Okay, this is an example of a big chip. Again, this crossbar kind of architecture. And you have these readout units. These MRUs are basically ADCs. Okay? They give some fancy name. From ISSCC always does this kind of stuff. Now, if you look at the power breakdown, the biggest consumer, blue bar, MRU, ADCs, 46% power. Okay, so you said, I'm doing very efficient computing, but you put ADCs there. Not a good idea. So you have to do something smarter about the ADCs. This is one example. You may say, maybe they did a poor design. Okay, so look at another one. This one is from IBM Zurich. It's a 64-core chip, and Giacomo would probably know this very well. This is a PCM-based device, but basically you can think of them as resistors. Okay, so similar. Their power breakdown, this side, blue bar, 50% ADC. Okay, so this is the story all across the board. You look at analog SIM devices, ADC is a killer. Coming back to your point. Okay, and also the area is pretty big unless you do it carefully, like I'll show you in a bit. Other challenges, system level challenges. This is another chip from IBM Almaden, also PCM devices, but a different group, Jeffrey Burr's group. And why I showed this, earlier in the talk, earlier in the workshop, Rajit was there, we were talking about Amdahl's law, something like that. So you see, this is TOPS per watt, energy efficiency of a single tile, one of these cores. That's what we normally report, right? That my core does very well. So they're getting 20 TOPS per watt. If you go to the full chip, you have to move data around the chip. Efficiency falls down to 12.4 TOPS per watt. If you go across 5 chips, then you're going up on a PCB across chips. Efficiency falls down to around 7 TOPS per watt. Okay? So at this point, you can see that improving the efficiency of a single tile, diminishing returns. Okay? So you have to look at the whole system and understand which part you want to improve to get full system level benefit. In their case, they had very tiny processing on a FPGA, which is very low tops per watt. They get something like this 5-chip efficiency in the end. So this also the extra digital processing, if this is more, you can see that this energy efficiency is a lot less, right? So if you do more of this, your full energy efficiency will get hurt. Where can they get hurt? Nonlinear operations. After the matrix vector multiply, we typically have nonlinear operations, which are typically done in digital. So like RNNs, like LSTM, transformers have softmax. All of these, if you're doing them in digital, a lot of digital computing, this big efficiency of the matrix vector multiply does not mean much. Okay, it's going to fall down. I'll show you that. Yeah. There is something called field programmable analog arrays, which use analog kind of computing in it. But this one they were using purely digital FPGAs. No, they're fully, the analog ones? Not really, depend, because you're comparing apples with oranges. Yeah, so it's difficult to say. But maybe that's a long question. That was topic of my PhD, so I can talk with you at length maybe after this one. Okay, so looking more again at system level challenges. This is a plot that we did one of our papers last year. This is looking at energy efficiency on x-axis, y-axis is throughput. And these red dots, I know it's not showing up very well probably because of the projector. The red dots are pure digital accelerators. Blue dots are in-memory computing accelerators. The circles are for CNNs, ANNs, those kind of networks which have less nonlinearity. The stars are for recurrent networks, LSTMs, which have more nonlinearity. And you can see there's a clear big gap. This gap is basically coming because Amdahl's law. So you're doing very nice matrix multiplies on RAMs or any device which is accelerating it, but then the digital processor slows you down or makes you inefficient. Okay, so you have a big gap whenever you have to do a lot of digital computing, which is not optimized. And basically this is another way to look at it, is look at the time taken, ratio of the time taken to do the nonlinear operation to the MAC operation. And you see this ratio is pretty big, even if you put up to 16 or 32 parallel digital processors. So nobody would put 32 parallel digital processors because it takes up a lot of area. But even in that case, okay, so simple way to understand what I'm saying is just look at this example. Suppose I had operations 100 cross 100 MAC operations and 100 nonlinear operations. It's like a 100 cross 100 crossbar. And then what I did using my crossbar in memory computing, I accelerate the MAC by 1000x. So now I only need 10 units of time for the MAC. The nonlinearity still takes 100 units of time. So now there's no point in making this MAC better and better. You have to do something about the nonlinear operations. Okay? So that's basically, I think in the rest of the talk, I'll talk a little bit about our work in the last year or so in addressing this. Yes? For this plot, each dot is coming from a, so this is a Boris Mormon style plot. If you're not familiar, basically each dot is coming from a paper in ISSCC, Symposium on VLSI or JSSC. So each of them have different voltages, different frequencies, whatever they're optimized. Point is to get an idea of a trend. Is there a trend? Is there a fundamental limitation that we can identify from here? Yes? So see, these are again, as we said, these are coming from very different designs. Huh? So that LSTM for RNN, the analog one, might be a very older design. This might be a very newer design. So it's difficult to say exactly why. But broadly, this is the trend that we can see. It's not catching up in terms of energy efficiency. Okay, so the first thing I'm going to talk about here is in-memory ADC for scalar nonlinear activations. Okay, so these are sort of nonlinearities that you normally get in a neural network, something like, these tan hyperbolic sigmoids and so on. So this work by these two students, collaboration with Chan Lee's lab at Hong Kong U. basic concept like this. Normal in-memory computing, you get this sum over Wi xi goes to a ADC. Then you have a processor for nonlinearities. This part is my IMC part. In this work, we merge the nonlinear computation in the ADC and then put the ADC inside the memory. So I use memory cells to do an ADC. Okay, so that's the basic novelty. Concept is like this. Those of you who have done analog circuits would know an ADC called ramp ADC. The way it works is, you have an analog input that I want to convert to digital. So what I do is I have a comparator. One input is Vin. Other input is my V ramp. What is ramp? You can see it's a voltage that increasing proportional to time. Okay? And then what I see is the time taken for the output of the comparator to flip will be proportional to this input value. Can you see that? If the input is lower, my ramp crosses the input faster. Yeah? And then it's very easy to digitize this time. You can run a counter and so on. So if you look at it mathematically, this output voltage is, this is theta is Heaviside function comparing the ramp voltage to Vin. So ramp I am writing as some function of time which is proportional to time in this case. And then what I'm looking at is time for the two signals to cross. So basically if I look at ramp minus Vin, I'm looking at zero crossing of this thing. So the time of the zero crossing is, if I look at this function, F inverse of Vin. So my question now is, nobody has told you that this has to be a ramp. What if I change the shape of this function? What if I make it some nonlinear function? What will happen? So now you see what happens here is, again from this equation, the zero crossing time is actually inverse function of Vin. So suppose the inverse function exists, then what I'm computing here is some g of Vin, some nonlinear function of Vin, where this nonlinear function is actually inverse of f. So now you can flip it and say, hey, if I want to create a desired nonlinear function, I know how to choose my ramp shape. It has to be inverse of the desired nonlinear function. And there are mathematicians here, they will say inverse, so does the inverse function exist? So of course this is I'm doing for smooth functions where inverse exists. Where it doesn't exist, we have also shown that you can break it up into piecewise invertible and you can do it. Longer discussion. They're in the supplement of our paper. So basically it means choose the ramp shape wisely. So if you want to do sigmoid, this is my inverse function of the sigmoid. That's how your ramp should look like. And then you can actually look at many different functions, nonlinear activations that are common. People these days tweak a little bit, say, transformer, I'm getting a little bit higher because I chose swish or gelu, whatever. So you can do all of that. Okay, so you can think of it. So now what about the implementation? How do I implement this? This is kind of a high level of our implementation. This was a RAM device. This was actually the original, those of you who have read the HP memristor paper, this was one of those devices, analog memristor array. It's a pretty old process, but these are analog memristors, so you can program them ideally to any value. And this is the memristor array to create the MAC part. I have one extra column of memristors which I used to create my ramp shape. Because I have RAM, I can actually program these ramp shapes according to what I want. So the way it works sort of is, you have these integrators where I'm integrating the charge from the RAM. And then this is my comparator that is comparing this output with the ramp. So this integrated output is my ramp. So in the beginning, I have some pulse width modulated signal that creates these outputs. After that, I start my ADC, these blue memristors, and I put them one by one clock after other to create the ramp shape. Key thing to remember, okay, if you look at the ramp shape, then what's happening, each of the steps, the delta of the step is different. Normal straight line ramp, every delta is same. What's happening then is for each of these deltas, I can program the conductance proportional to this delta. Because I have memristors, I can program these steps to be different. Okay? So I still need just one device per step, and I just program the values according to the required delta. Just to show you a little bit better, this is the first part where you have the MAC, and then after that, you can actually start your ramp one by one. Okay? And you have different step sizes according to what nonlinear function you need, inverse of that. Okay, so how does it look like? Theory is very good. When you measure, things look a lot different, especially in a big chip across many devices. This is example of a sigmoid. You do have a lot of variations. There are some calibration tricks that I can talk with you later on. This is example of conductances that are mapped for sigmoid. These are the calibration conductances. So you can see there are some programming errors, and then you see some black devices. These are actually stuck devices, devices that you cannot program. Okay, you will get some faults like these. So again, you need to do something to be fault tolerant, and again, we have several strategies in the paper. Another good thing about this approach is resilience to variations. In this case, we are simulating cases where the read voltage has some fluctuations, which is generally true if you have a big chip with many cores. The read voltage that are going across the core, you'll have some IR drop effects, and you may have some variations. So you see that the middle red line is our case with all the variations. You have little bit of effect. Normal ADC really goes all over the place with these kind of variations. What's happening here? What's happening is our bit cell that is creating these steps is matched with the bit cell that is creating your multiply and accumulate, MAC. So because of this inherent matching, to a first order, we get cancellation of any non-idealities. So this is called replica biasing and with analog circuits, and basically that's what helps us to cover these PVT variations very nicely. Yeah. Yeah, it's very much possible. That's basically, if you have a 1-bit ADC and then you reset the bit line again and allow it to integrate again, that whole thing becomes effectively like a sigma delta. So you can also do that. Yeah, possibly. You can also do something like a CCO, current controlled oscillator based ADC. So instead of resetting the bit line, you can have something else. But maybe we can talk about that a little bit later because I'm almost out of time. Yeah. I just wanted to show a few more things and then we can talk about this offline. Okay, so finally, whole thing put together, this is a real application for keyword spotting, an LSTM for keyword spotting. And the reason for doing this is, benchmarks, and you have to compare your result with other people in ISSCC, Nature, and so on. So this is a 5-bit ADC, this is 4-bit ADC, this is 3-bit ADC. And these were pretty much state of the art at that time. One of this is Shichi's work actually. And you can see that actual chip test with all non-idealities put in, you can get something like 89% accuracy. It's good, but we can do even better. So this one was RAM. We did actually, let me just flip over this. Oh, so this is important. This is looking at the energy efficiency. And you can see that we did improve efficiency quite a bit. Okay. So both in terms of area efficiency and energy efficiency, because entire nonlinear operation, everything is now in memory. You don't have to go outside the memory at all. Okay, so that's the trick. And since I'm running out of time, let me quickly go to the SRAM version. So same concept you can do in SRAM, but there are very interesting differences. So this paper also just came out in JSSC, so you can take a look. Moral of the story, let me just quickly go to the moral of the story, is if you compare SRAM with RAM, what's happening is SRAM chip, you can get even higher accuracies of close to 92% on this data set. SRAMs, you would normally think you have quantization error, right, for the ADC bit step. Turns out that for the RRAMs, typically the amount of write noise that you have, it overpowers all quantization error and mismatch error in these SRAM-based in-memory cells. So accuracy-wise, SRAM wins 1-0. Energy efficiency. If you compare, again, this is our RRAM work with the SRAM work. SRAM gave you 5.2 times better energy efficiency. So SRAM 2, RRAM 0. So where does RRAM then win? RRAM wins in terms of area efficiency. So the area of the SRAM device was a lot bigger than the RRAM one. Okay, so that's kind of what we have found so far in our comparisons of SRAM versus RRAM. Same task. Yeah.
These SRAMs are assumed to be far away from the computing unit, right? They're not like distributed near memory.
No, these are in-memory computing SRAMs, but far away from compute unit, meaning if you're saying is it next to a CPU or not?
It is next to the whether it is next to the compute unit which is doing the inner product.
The memory is doing the inner product.
So this in-memory SRAM.
Yeah, it's in memory. So I didn't show you any near memory stuff yet. Yeah.
So do you have a snapshot for the SRAM based architecture like the one you showed for VRAM?
I can go over that. I can, just after the talk, maybe I can talk with you and show you. But this one is important because softmax, somebody talked about softmax. Yeah, okay, yeah.
Sorry, I was just wondering what is the pitch of the amplifiers at the side? If that's large, then it's okay to have large area for the SRAM compared to the...
Pitch of the amplifier?
Yeah.
There's no amplifier here per se. So for the SRAMs, so actually I should have, let me go back once. For the energy efficiency part, why do I get 5.2x better? Because I do not have transimpedance amplifiers. That is the bottleneck. Okay, for RRAMs, you need a TIA. SRAMs, because it's a transistor, not a resistor in the bit cell, it acts as a current source. So that's the active device for you. Yeah. So that's why I don't need a TIA, I get this energy benefit. Okay, so last one is, sorry, I'm going a little bit over time, 5 more minutes. This is vector nonlinear functions, softmax, because everybody doing transformers likes this. I think yesterday, the talk on Ising machines also, somebody talked about softmax, right? I think they were using. So very, very popular thing. And it also ties in with probably the closest neuromorphic construct I have here, which is a winner-take-all. Okay, so it's a winner-take-all structure, is a competitive network. For those who are not familiar, basically it's like, think about I have n values and I want to choose which is the largest value. Or a generalized case is saying a top k out of these n largest values. Okay, very common computational construct, very widely found in the cortex. I think Giacomo has a lot of work on this, but basically you can see stuff like, inputs being projected onto some excitatory neurons, and then this inhibitory neurons will inhibit other layers, other parts which are not most active. Okay, so you can actually reduce or refine your representation a little bit, if you like. But in reality, of course, it's a lot more complicated than this. I won't go into this. So this has a tie with softmax. Where does it tie? So if you look at softmax, I hope a lot of you are familiar with it. It's basically an exponential, right? E to the power xi, and then you divide by sum over e to the power xi, something like that. In digital, computing this, okay, it's rolled out in the front. No worries, no worries. So if you think about this exponential, that's difficult to do in digital. Now think about what happens. Because of the exponential, if the input to the softmax is a vector, the larger values amplify up, smaller values get squashed down to 0. So basically you have a bunch of zeros and a few values which are large. So then that gives you an idea. If I can find out what are the top k values going into the softmax, maybe I can just compute the exponential for these k values, not do it for the others. And that's going to save a lot. It's a good approximation to the softmax. Okay. So it turns out people in digital have tried this, and the problem in digital is you have to do a sorting to find out these top k values. That now takes up time, energy. So now I show you an example of how you can do this winner-take-all, sorting everything in memory using the exact same ADC array that I have shown. So now I reuse my ramp ADC architecture, but instead of an upgoing ramp, I create a downgoing ramp. Okay? So now think about it. if I have a set of input voltages that I'm comparing with the ramp, the largest voltage will cross the ramp first, right? So basically now I can look at events of ramp crossings and I can stop the moment I get the first k events. So very easy. So sorting for free. Okay. Advantage now, I don't need sorting. Secondly, the ADC array, I don't need to run the rest of the ramp. I can just shut down everything. So I also save ADC conversion energy and latency. So benefits all across the board. So this is showing an example. This is a ramp ADC and this is early stopping. I save the latency of this part. Okay, so I hope you got the idea. So I think this is what we are doing. So for softmax, I only calculate k exponentials now. It's your favorite transformer block, self-attention. And where we are doing this is in this q.k transpose part. Why? Because this part you're updating every cycle. So you can't do using RAM. You have to do use SRAM because you have to write every cycle. So this was a SRAM accelerator using this in-memory winner take all for softmax. I think I don't have time to do more. So let me just skip this. Again, this is a paper in TCAS1. We can take a look. And you have a lot of different comparisons. So our architecture is super good compared to all other methods of doing softmax. Orders of magnitude better. Orders of magnitude. Okay, so this is really, really good. And because winner take all is useful in many, many cases, you can now expand this. Ising talk yesterday. You can actually use this in that same Ising architecture. Very, very useful macro, and now we are kind of using it in many other things. So next year, hopefully when I'm here, I'll show you more interesting stuff. Okay. So there are some other stuff I had about, okay, one last thing. One last thing. I think this is important because earlier I told you bit slicing is very good, right? So now I'm going to tell you the problem of bit slicing. And then that's it. I'm done. So pulse width modulator for the input DAC, I told you the latency is 2 to the power n, yeah, 2 to the power n clock cycles. So now look at it a little bit closer. There is a latency of input bit resolution, Ni is number of input bits. There is also a latency of output bit resolution. My ADC, ramp ADC takes 2 to the power n clock cycles as well, yeah. So I'm calling that NO, number of output bits. So if you have a pulse width modulated kind of system, you have 2 to the power Ni clock cycles to create the input, and then the voltages are held on the capacitor, and then you need 2 to the power NO cycles to run your ADC. Okay, so that's this PWM mode, the blue line. This is plotted against input and output bit number, which I assume to be same here. Bit slicing, what happens? You give one bit, then for that single bit, you have to run your 2 to the power NO clock cycles for your ADC. Second bit, again 2 to the power NO clock cycles for ADC. N bits, you need N times 2 to the power NO clock cycles. So you thought bit slicing was good, but at that time we did not think about the output ADC part. So you're running the ADC every time for every bit. That is actually not good. So this bit slicing mode turns out actually has more latency than PWM mode. Okay, so that's why again you have to look at the whole system and then analyze. So our method improves on both of that. How do I do that? Quick thing. Basically, again, I'm an analog guy, so I use analog accumulator before the ADC. So I don't run the ADC every time. Instead, we figured out a way where you can use charge sharing using two capacitors to give you the exact weighted summation, power of 2 weighting summation that you were doing in digital. Power of 2 weighting is same as if you have two capacitors with same magnitude, you just charge share across them, you get division by 2 for free. Okay, so basically that's what's going on. So after each of the bit lines, we have a set of 2 capacitors, and after every bit, you do a charge sharing. So after the entire n bits, I will run my ADC only once. Okay? So this is the best method so far, and I mean, there's some math here. You can look at partial sums and non-idealities of this capacitor array and so on. So not going to go into that, but basically it's the same kind of power of 2 weightage that you want. Latency is now number of input bits plus 2 to the power n. So best of both worlds. Okay, I think let me stop here and just look at conclusions. And it's one big picture here, right? I'll come to this at the end. Basically, what we have talked about so far, in-memory computing good for increasing energy efficiency and throughput. ADC, big overhead. I showed you a lot of ways in which you can put the ADC inside the memory. Didn't have time to go over those big tables, but basically what it shows is in-memory ADCs, the area required is much less than conventional ADCs like SAR or Flash if you put them outside. Nonlinear in-memory ADC is good, can implement direct nonlinear activations. Winner take alls, also I showed you how they can be implemented inside the memory. And in my group, basically I'm looking at exploring things apart from matrix vector multiplies. Okay, and there are many signal processing computes that you can embed in here. That to me is interesting, right? And just increasing a little bit efficiency in MVMs is not so much interesting anymore. Okay. Why did I put this last plot? Again, same thing I talked about earlier, Amdahl's law. Think about system level efficiency. There was a nice survey paper that came out which looked at x-axis is macro level energy efficiency. That's one single block that everybody reports. Y-axis is system level energy efficiency. And you can sort of draw a straight line through here. I mean, drawing lines through data, always there are jokes about it, but anyway, you can kind of draw a line through this one. And basically you see like this point where you have about 30 tops per watt. This side is about 12 tops per watt at system level. Okay. So at the system level, when you're communicating data all around, you basically lose a little bit more than half of your energy efficiency. Okay. So be careful about the whole system. Don't just design your single macro. Okay. So that's the main message I wanted to give. That's it. Thank you very much.